Hi, it's Monday, June 8th, 2020. My name is Noah Seeley, and welcome to my channel. As we continue to follow our series in visualization machine learning models, I thought a good topic to discuss is not just image classification, but a little deeper into object detection within an image. What this topic generalizes to are models that can take an image as input and detect specific objects which can be found within that image. For example, if we put an input of an image of a dog and a cat on a boat, a trained object detection network would be able to identify roughly where the dog is, the cat, and maybe even the boat. This identification is usually visualized as output of putting a box around the region where the model thinks the object is. Thus, there'd be a box around the dog, labeled dog, a box around the boat, labeled boat, and a box around the cat, labeled cat, if all went correctly. So the object detection related paper I want to discuss today is written by Richard Girshick at the Microsoft research team. This is called FastRCNN. So without any further delay, let's jump into it and see how the team was able to produce an effective object detection model. So this paper begins with listing off the reasons why object detection is a more difficult task than image classification and some of the drawbacks from previously made detection models. Let's quickly cover both of these points. Detection is more difficult than simply classification because object must not only be classified, but also located accurately in the given image space. The typical detection algorithm usually goes like this. Some new candidate object locations in the image, which we'll later refer to as proposals, must first be processed. Proposals only provide rough localizations though, and they must be processed more precisely to be located and then classified. Ultimately, the model learns to classify objects and refine their spatial locations, all using a convolutional network. So although this algorithm is in place, previous detection models suffered drawbacks such as their training time was a multi-stage pipeline, their detection was slow, and their training was slow. The paper uses examples of these drawbacks with other detection models such as spatial pyramid pooling nets and RCNNs, not to be confused with fast RCNNs. We won't worry about those too much here, but it is important to note that the paper proposes a detection model that can do all of those things we talk about in a detection algorithm, but without the drawbacks of those other models. It's called the fast RCNN. The fast RCNN promised higher detection, single stage training with multitask loss, training updates on all network layers, and no disk storage. So what this basically means is they're going to make a stronger and faster update to these previous detection models. So with that all being set up, let's delve into the techniques that the fast RCNN used to be such a superior model to its predecessors. Fast RCNN takes the input of a single image, which it will be detecting upon, and a set of object proposals, which are proposed locations of objects it may detect. It roughly follows the following algorithm to process the detected images. So the first step is that the model will process the input image with convolutional layers and max pooling layers to produce a feature map. The second step is that for each object proposal, a region of interest, known as an ROI, pooling layer, extracts a feature vector from that original feature map in step 1. Each of these feature vectors from step 2 are fed into a set of fully connected layers that branch out into two outputs. The first output is a softmax probability estimate over k+1 object classes where the proposals may be. The +1 to k is a catch-all background class for classifications that might not fit into any of the other k classes. The other output is another layer that outputs 4 numbers for each of the k object classes. Each set of the 4 values encodes a position to set a bounding box over the object in that image. So overall, the model will process the image as a whole, and then from that process each individual object within that image, outputting probabilities of which object it thinks the selected object is from a set of k possible classes, and a bounding box around that object in the original image. The paper then explains more technical bits of each of these steps, which I'm just going to leave out here for sake of simplicity. Just remember that I've linked both the paper and its GitHub repo in the description below, and I'm willing to make another video on the more technical side of the architecture if anybody wants it. So now that we've been introduced to the fast RCNN structure, let's see if it actually lived up to its hype. The results section discusses that the fast RCNN is able to achieve top results with the VOC 2007 and 2012 dataset competitions, compared to the predecessors such as the RCNN and the spatial pyramid pooling nets. It also mentions that the SegDeepM model also performed better when it was used with the fast RCNN rather than just the RCNN. Those results take some prerequisite knowledge, but the important takeaway is that the fast RCNN was able to blow its previous competition out of the water, outperforming these models in a variety of competitions. They were also able to achieve faster training and testing times, as well as use less space than the previous models. The team also comments on how they had to train their convolution and ROI layers and fine-tune a few of the convolution layers, but not all of them. As for best practices, they found that the softmax activation function outperformed the SVMs, and that the more training data they had, the better the model would perform. They also commented that sparse proposal sets increase detection accuracy compared to dense sets. Basically, this means that it's good to reject a lot of the original object proposals and just go with a smaller set to process. So yeah, that's my take on the fast RCNN object detection model. It acted as an update to the RCNN and SPP net models, and with the discussed algorithm and training improvements, was able to outperform them in a variety of competitions. A similarity to this paper and the ASCE paper that we reviewed a few days ago is that they mention as technology becomes more and more advanced, so will both classification and detection models. This means that machine learning will continue to improve, and soon we may even see that the fast RCNN model is being updated and outperformed, which is both exciting and a little scary to think about. So that concludes my discussion on the fast RCNN paper by Girshick and his team at Microsoft. There are more technical bits, as I mentioned, of the architecture that I did not delve into. So as always, I've linked all the resources that I've used in the description below for you guys to check out yourself. If you feel that I've missed anything or got anything wrong, please let me know in the comment section below. That's all for today. Thanks for watching. See you tomorrow.